Much of our work in organic chemistry involves trying to understand the three-dimensional structure of molecules and inspecting the distribution of electrons within those molecules to predict how they might react and behave. Now, the organic chemist has many different tools for analyzing the distribution of electrons within a structure. Today we're going to discuss formal charge as one of the most important and simple tools for understanding structure and reactivity. Think of formal charge as a bookkeeping method to quickly judge whether an atom within a molecule is neutral or bears a positive or negative charge. If you look in a textbook, you find a lot of different formulas to calculate formal charge, but I wanted to try to understand this conceptually. To calculate formal charge, we begin with one atom at a time in a Lewis dot structure. For each atom, we compare the number of electrons owned by that atom in the Lewis dot structure to the number of valence electrons that atom would possess in its neutral, isolated form, not bonded to anything else. If the atom owns more electrons in the Lewis dot structure compared to valence electrons in the isolated atom, we say the formal charge is negative. On the other hand, if the atom owns fewer electrons in the Lewis dot structure than valence electrons, the formal charge would be positive. Let's look at a few examples of this in practice, starting with water. In the Lewis dot structure of water, oxygen has two lone pairs and two separate single bonds to hydrogen. To determine the formal charge on oxygen, we subtract the number of electrons oxygen owns in this Lewis dot structure from the number of valence electrons it would have as an isolated neutral atom. But what does it mean for an atom to own electrons in the Lewis dot structure? Let's start with lone pairs. Because these electrons are not shared with any other atoms, they are considered non-bonding electrons. They are owned exclusively by the atom they reside on. Because each lone pair contains two non-bonding electrons, and there are two lone pairs here, we have four non-bonding electrons owned by this oxygen atom. Now what about bonding electrons? When we calculate formal charge, we assume atoms share electrons equally in covalent bonds. That means for every single bond, which represents two shared electrons, one electron is owned by one atom, the other electron is owned by the other atom. Another way to say this is that an atom owns half of its shared electrons. In practical terms, this just means we can count each single bond as contributing one electron to a particular atom. With oxygen having two bonds to other atoms, that equals two bonding electrons owned by this oxygen atom. Accounting for both non-bonding and bonding electrons, this oxygen owns 6 electrons. What about valence electrons? Using the periodic table, remember that oxygen has 6 valence electrons in its neutral form. And when the electrons an atom owns in a structure matches its number of valence electrons, the formal charge is 0. The atom is considered neutral. Now we can determine the formal charge for any atom in a Lewis dot structure. Take hydrogen here as an example. Hydrogen has one valence electron in its neutral form. It owns one electron in the structure of water, which equates to a formal charge of 0. Stepping back then and looking at water as a whole, we see both oxygen and each hydrogen have formal charges of 0. This should make sense because water is a neutral molecule and the sum of the formal charges on all atoms should always equal the overall charge on the molecule or ion of interest. Let's see how this could apply to a structure that isn't neutral. For example, hydroxide. Here, the hydrogen is unchanged, so it still has a formal charge of 0. But what about that oxygen? Well, oxygen always has 6 valence electrons in its neutral form. That never changes. But how many electrons does this atom own? Here it has 6 non-bonding electrons and one single bond, contributing 1 electron. That's 7 electrons owned by this oxygen, which leads to a formal charge of -1. That should make sense because hydroxide is a polyatomic ion with an overall charge of -1. Let's go in the opposite direction now. Instead of looking at a structure like hydroxide, where oxygen owns more electrons than valence electrons, consider the structure of hydronium, where oxygen is forced to share more electrons with hydrogen, and as a result owns fewer electrons. Again, the hydrogens here are unchanged, so each are formally neutral. But what about that oxygen? It has 6 valence electrons. It always does. But in this case, only owns 2 non-bonding electrons and 1 electron per bond with 3 bonds to hydrogen. That's 3 bonding electrons it owns. That's 5 electrons total. 6 valence minus 5 owned equates to a formal charge of positive 1, which again should make sense because hydronium is a polyatomic ion with an overall charge of plus 1. Things can get more interesting with multiple bonds, but the analysis works the exact same way. Whenever oxygen has 2 lone pairs and 2 bonds, its formal charge will be 0, just like in water. It doesn't matter whether there are 2 single bonds or 1 double bond. Similarly, whenever oxygen has 1 lone pair and 3 bonds to other atoms, it will always have a formal charge of positive 1, just like in hydronium. We treat double or even triple bonds the same way we do single bonds. Each bond contributes 1 electron owned by that atom. Now let's inspect a molecule that has an element other than oxygen, like ammonia, NH3. First, we don't usually bother writing the formal charges on neutral atoms, so we know all those hydrogens are good to go. But what about the central nitrogen atom? Well, unlike oxygen, nitrogen only ever has 5 valence electrons in its isolated neutral form. How many does it own in this Lewis dot structure? Just like in the case of hydronium above it, there are 2 non-bonding electrons and 3 bonding electrons for a total of 5 owned electrons. 5 valence minus 5 owned equates to a formal charge of 0. This means ammonia is a neutral molecule, whereas hydronium is a positively charged ion. Why? Because of its position in the periodic table, nitrogen only ever needs to own 5 electrons to be neutral, as it is here. Oxygen, on the other hand, needs to own 6 electrons to be neutral. In the case of hydronium, oxygen only owns 5 electrons, making it positive. To drive home this point, let's look at another structure bonded in the exact same way, but with carbon as the central atom. According to its position in the periodic table, carbon has 4 valence electrons in its isolated neutral form. How many electrons does it own in this structure? Well, we already know. 1 lone pair, 3 bonds, that's still 5 owned electrons, just like ammonia and hydronium above it. But in this case, carbon owns more electrons than it would have in its isolated neutral form. 4 valence minus 5 owned equals a formal charge of -1. That doesn't mean nitrogen will always be neutral or carbon will always be -1. There are plenty of cases where nitrogen exists in a bonding arrangement where it is formally +1. In other cases, as the number of owned electrons varies, nitrogen can have a formal charge of -1. Carbon as well has many different bonding arrangements where it can have a formal charge of -1, 0, or +1. What would those look like? How could we double check the formal charge with a calculation? These are the fundamentals we will build on to explore the structure and reactivity of organic molecules. With a little practice, formal charge can be a powerful tool to understand and predict the outcome of reactions in organic chemistry.